Hi, welcome to lecture 21. This is going to be about banking and banking angles. And this again is really an application of the things we've learned so far, so there are no fundamentally new concepts here. We'll be applying what we know to some new scenario. So we'll talk a little bit about driving around a turn, right? So we mentioned in a car, but it would equally apply if you're on your bike, for example. And you drive around a turn, just a normal sort of flat road, without what's called banking. Then we're going to introduce banking. Banking is when the road is not flat, but essentially at a slight angle to make it easier to drive around turns. So we'll discuss exactly what that is. We'll find the ideal banking angles. We'll play traffic engineers for a bit and pretend we're trying to build a road here, maybe part of a highway stretch. Well, how should we build that road? Of course, and the answer we're going to get here is a little bit outlandish, I suppose. So we'll look at some slightly more realistic way of implementing banking, say, along a highway and figure out what the consequences are. Let's talk about driving around a turn first. So here's our car and we're driving on the road. I guess we're driving on the wrong side of the road, but who cares? On the turn. So what force allows us to turn? Now, you might be like, okay, how can I think about it? Well, one way to think about it is ask yourself, well, under what condition might I not be able to turn? For example, if the road is icy, that kind of gives you the hint. What you need is friction between the tires and the road. Right, so friction, static friction specifically, that allows us to turn. So static friction provides the centripetal force, because we want to turn, so we will have a centripetal force. Right, so in this case here, the static friction between the tires and the road, and based on how the tires want to rotate and based on their position, they'll want to, if the car were to go in a straight line, they would need to slide if you turn your tire slightly, and because friction opposes sliding, the friction in this case actually helps us turn. So the static friction in this case points inwards. Why is it static? Isn't the car moving? Shouldn't it be kinetic? No, because the car is moving, but the tire itself is not sliding along the road. But it better not, right? Otherwise you're in trouble. Let's figure out how you turn here. So the free body diagram here is fairly straightforward. We've got the car has a weight. It's of course down. We write mg, you know that's the weight. There's a normal force from the road. We're not falling into the road. You can write Fn. We've used it often enough, so you know what that is. And then we have the friction, and in this case, the way I've drawn it, the friction is going to point this way. This is going to be static friction. Okay. So how big is static friction? Well, it's as big as needed, right? So let's ask, how fast can I turn? What's my maximum speed without sliding? And imagine if I go too fast, I would slide, right? So you could slow down before you reach the turn. So this is the force that's going to make me turn. So I want that static friction. I want that to be equal to mv squared over r, the centripetal force, right? And m, of course, the mass of the car. But static friction is going to be, at most, its maximum, right, is, write like this, smaller or equal to mu s, the coefficient of static friction, times the normal force. And in this case here, the normal force is just equal to the weight because there's no other force up or down, and the normal force acts straight up because the road is flat, right? It acts perpendicular to the road. The road is horizontal, so the normal force is vertical. So mu s times mg. Right, so what that implies is that I have that mv squared over r is smaller or equal than mu s times mg. Now you notice I can cancel out the m's, so actually the maximum speed is independent of the mass. And I find that v squared has to be smaller or equal to mu s times g times r. And if this is not true, then I'd slide. Otherwise, you'd slide. This allows you to calculate the maximum speed. I guess I could write it like this. Mu s times g times r. Right, where of course v can be as any value from 0 up to, well, that maximum where we have an equality here. So if, say, r is, say, a long highway curve, like 100 meters, of radius, right? So if this is a part of a circle, of course it's not a full circle, it's unlikely, but then I could sort of find the radius of this turn, and let's say it's 100 meters, might be like for a fairly big road, that's, I guess, a realistic value. G is, of course, 10. Mu s, what's mu s? Let's suppose it's about 0.9. Fairly dry road, rubber on dry road, tires on concrete. About 0.9, I guess it's a realistic estimate. So that implies that I have that v, the speed, the max speed, well, v is smaller or equal to, so if it's equal to, I have the maximum 0.9 times 10 meters per second squared, that's g, times 100 meters. Tell the units are meters squared, meters and meters per second squared. So take the square root, you just end up with meters per second. That's 900, square root of 900 is 30 meters per second, which, if you want to know, it's about 67 miles per hour. Right, so on a flat road, under those conditions, 100-meter radius turn, that's your maximum speed. Otherwise, you would start sliding. And that's the kind of calculation when you're an experienced driver, you kind of do in your head. You don't actually do the calculation, of course, but you sort of intuitively try to figure out how fast can I go around this turn. One thing that's interesting is that the maximum speed, like v squared, relates to r. So if I want to drive twice as fast, I need a curve that's 4 times as big to be able to do it without sliding. Okay. Now suppose you want to go faster around a turn, right? Well, friction clearly is not enough. So that's where banking comes in. So banking means we take this road and we tilt it like this. Now, there are extreme cases of banking where it isn't about a road, but if you watch like indoor cycle races where they go like round and round and round and round, say some kind of Olympic discipline or so, they have these, their track is like really steeply elevated because they go around so fast, it's almost like just pushing against like a vertical wall. Not quite, but it's kind of how it feels. So we might do it with the road too to allow us to go faster around a turn. If we do that, it might look something like this. I'll try to draw this here. Okay, now we're just driving in the middle because we don't care. So you can see I've drawn the road at an angle. So why is that going to help us? It's going to help us because now the normal force is going to act inward. Let me draw a free body diagram here. So here's my road, right? It's at some angle. This is exaggerated the way I've drawn it. And the angle is going to make the road here make some angle theta with the horizontal. We'll actually try to figure out in a moment what angle theta to pick if we are the traffic engineers who are trying to build that road. But let's analyze the forces on the car. There's the weight down as always, because this is on Earth, or at least on the planet. Can't have roads in space. And then I have a normal force. So a normal force in this case is going to be in this direction. Right, perpendicular to the surface. It's normal. Now what this means, my normal force now has a horizontal component and a vertical component. This one should be straight down. Right, so the horizontal component, vertical component, and the vertical component is going to cancel out the, if you do it right, it's going to cancel out the weight, and the horizontal component is what makes us turn, right? So it has a component like this and a component like this. Let me draw it like this, right? So the two components of the normal force. This would be Fn, I guess y, and this is Fn x, if I pick my coordinate system to be y and x. Right, so in this case, even though I'm dealing with something on a ramp, or an incline, I'm actually going to pick this coordinate system here. Why? Because I know that my net force is going to be to the right. Right? Because what I want to do is I want to get around my turn without sliding up or down. So I want to maintain the same height and only turn. So in this case, I sort of come towards us here like this. Right? Hard to show in 3D in the video. Hopefully you can visualize what's going on. Right? So I want the net force to the right. I don't want the net force up or down because I want to stay at the same height and not slide up or down on the street. Okay, so I hope this setup makes sense to you. Now, ideally, I want to be able to make this turn without any friction, right? This is what I mean by the ideal banking angle. Let's write this down. The ideal banking angle is the angle where we can make the turn without friction. Now, how can you think about that? Well, imagine the road was covered in ice, right? Now, if you're coming along the road, you're driving, like, oh dear, it's all covered in ice, what shall I do? Well, you need to hit the right speed. If you're going too slow, you'd imagine you sort of slide down and end up, coming this way and sort of sliding towards the inside. If you're going too fast, you'd be sliding to the outside. I hope that just makes intuitive sense to you. Of course, when the road is not covered in ice, we have friction to help us along, and we'll talk about it in a bit. But we're going to find the ideal angle where I can go on the turn without any friction, without having to use friction. So we imagine maybe the road is covered in ice, like what speed would you get? Of course, actually, the logic is the other way around. You're going to say, well, look, here's a stretch of road, and the cars are going to go, I don't know, let's stick with the 30 meters per second that we had before. Right, so at what angle should I build my road to allow cars to go at that speed? Right, the ideal banking angle depends on the speed of the vehicles going along that stretch. So we want to find the ideal banking angle for a stretch of road where the average speed is, let's call it V average, 30 meters per second. So 67 miles per hour, a sort of stretch of highway, I suppose. So what is the ideal banking angle? Well, let's write down our equations that we get from this. In the x direction, right, in the x direction I only have one force, namely the normal force, the x component of the normal force. With a bit of geometry, I can easily see that this angle theta is the same as this angle theta here. It has to be, because this here is 90 minus theta, this is 90, so this is again theta. Make sure you understand that, how I can say that this angle here is theta, right, just from the geometry. So I have that in the x direction, let me write it like this, I have that F net, the x direction, is just the normal force in the x direction, which I can see here, this component, or maybe this component up here, so Fn times sine of theta. I want to emphasize that because the car is moving, I can't assume that Fn is just mg cosine theta, like it was the case when we talked about stuff sliding down ramps, for example, or maybe not sliding because of friction and just sitting there, right? This is a different scenario. Here, there is motion, there's a non-zero net force, so we can't make this the assumption that our earlier result applies. In fact, it doesn't. Right, so this is my net force in the x direction now. And we know what it is equal to. That's going to be equal to mv squared over r. Right, because it's a net force, and that's the thing that makes us turn. It's the centripetal force. The normal force, or the x component of the normal force, acts as the centripetal force. In the y direction, I know that's going to be 0. I know it's going to be 0. Actually, let me write this on the far right. And over here. I know the net force is going to be 0 in the y direction because my car is not moving up or down. Right? If we're moving up or down, it would either have to take off or sink into the ground. That's not happening. Or at least it would have to sort of slide up or down. And again, it's not happening either. What is the net force in the y direction? Let's have a look. Well, it's going to be this up and this down. So I can write maybe f n cosine theta. Again, that's this vertical component here. Minus mg. So from this I can see right away that a normal force must be equal to mg divided by cosine theta. Right, just by saying this is equal to 0, I can solve this for the normal force. Okay, so knowing this, I can now plug it in here. I'm going to say plug into x. I'm annotating what I'm doing in case I get lost or make a mistake. And then I get mg over cosine theta, that's this part here, times sine theta is equal to mv squared over r. Right, so I've said this is equal to this, and I've replaced the normal force with the expression I have from knowing about the y direction. Alright, so now I can just simplify this. The m's cancel out. Again, that's convenient, right? It means my banking angle doesn't depend on the mass of the cars. That's good, because I expect there to be little sports cars, large trucks, and everything in between. So to go along my stretch of road. So I can rearrange this because sine over cosine is tan. So I'm going to get tan theta is equal to v squared over r. There's a g here. The g goes down to the other side over gr. R was 100, g was 10, v was 30. So if I plug those values in and my calculator doesn't fail me, this is going to be 30 squared, 900 over 10 times 100, so it's 900 over 1000, that's 0.9. Inverse tan of 0.9 comes to about 42 degrees. Now that is pretty steep, right? That is like 45 degrees like this. So this sort of actually you build the road like this. I mean, you don't see any roads that are actually that steep, right? But ideally, if you really want to go around a turn at 30 meters per second, about 67 miles per hour, without relying on friction at all, if you're covered in ice, we'd need an angle that's that steep. And maybe you'd actually implement that if you're not talking about building a road, but maybe building a roller coaster and you want to go around a turn. Right? So if you visualize a kind of roller coaster, the old ones where the cars are always sort of flat and then you get bumped left and right, it's kind of uncomfortable. But the more modern ones tend to have you're sort of angling like this way and that way, depending on which way you're turning, because it creates a more comfortable experience. Because you experience a normal force that makes you feel a bit heavier, it pushes you in your seat, but not these sort of sideways jerking. But for a road, that is way too steep. Like that would not be safe for all sorts of other reasons. So more realistically, what you might do, you might rely on both friction and the banking. So realistically, we might rely on a combination of friction and banking. And banking, of course, implying that we're part of a normal force that helps us make the turn. Okay, so what would that look like? So here's my hill. So I'm probably going to pick a hill that's not that steep. Right, it's more easily built, more stable piece of road. Stuff won't just roll down it sideways. This is some smaller angle, theta, say. Right, so now not 42 degrees, it is just some angle. Not the ideal one, just some angle. So here's my car, and what forces are acting now? Well, there's the weight, there's the normal force, and then there is friction. Now, which way does friction act? Well, here we have to remember static friction opposes the sort of attempted acceleration that would be there without the friction. It opposes sliding. So if I was going around a turn and the angle was too small for my speed, right? We made the angle smaller than it should have been for the ideal angle. Well, that means I'd be sliding outwards. So that means friction is acting inwards. I'm going to use purple for friction. So the static friction would be acting this way. Why is that? Well, static friction opposes sliding. Without it, the cars would slide outwards. Right? They would say, like, the turn is sort of coming this way. Right? If the car is coming towards us, like this, it's going to turn in this direction. So your car would slide this way if this was a sheet of ice. Static friction opposes that, and so it acts inwards in this case. If on the other hand you were going too slow for the turn or the angle was too steep, then static friction would stop you from sliding down the hill, but that's not the case that we have here, because we made our angle smaller. This is fairly subtle, this logic, so make sure you understand it before you move on. How did the car slide outwards? So static friction, we write SF, acts inwards towards the center of the turn, opposing the sliding. Okay, hopefully that makes sense. So let's do the rest of the geometry here. This angle here is going to be also theta, just like we had before. And again, it should be clear that this angle here is also theta. The angle with the horizontal. So hopefully you can follow the geometry here. Again, should be fairly straightforward. If not, pause the video, work with the triangles. Okay, what's this angle here? You get it. Okay. So let's see what happens in the x and the y direction. What am I trying to find? I'm trying to figure out, well, what's the maximum speed I can now go at for a given theta. Let's write this down. For a given banking angle, what is the maximum speed cars can go at? That's kind of the inverse from before. We found the ideal one. Well, now we're just given one that's more realistic. Well, how fast can I go? Can I go faster than 67 miles per hour? Right, that's our goal. What's the maximum speed cars can go at? Okay, so let's do the analysis here. So in this case, I've got 4 quantities to worry about, 4 vector quantities. I have static friction, I have the normal force, and I have the weight. Then what I want is I want the net force, of course, to be to the right. Because we don't want to slide up or down on the road. We want to stay in our lane. Right? So I want to not end up sliding down or sliding up and hit the trees on either side, or maybe another car in a different lane. Okay, so I've got two quantities that are horizontal or vertical and two quantities at these angles, so it's kind of which coordinate system do you choose? I'm going to go with x this way, y this way, because I like having my net force in only one direction. Right, it does mean I've got two forces that are now at angles, but, you know, it is what it is. You could rewrite this with the angled coordinate system, x down the hill, y perpendicular, and work through the math that way. It will give you the same result, it's just the algebra looks a bit different. Okay, but let's analyze this in this coordinate system here, where x is horizontal and y is vertical. So the x direction, what do I know? Well, I have that the net force in the x direction is, what is it made up of? The normal force, Fn, sine theta. That's the part we had before when there wasn't friction. But now we have friction as well, and friction's helping us. F static friction, right, SF, force due to static friction. Not the whole one, it's at an angle. I have to take the horizontal component. It's cosine theta. Again, make sure you understand why it's cosine, not sine, right? You can analyze this triangle, find this horizontal component of this static friction force. Always make sure you understand every step, so you can always pause the video. And then what's it equal to? Is it 0? No, it's not 0, because we need a sideways net force. It's going to be equal to mv squared over r, because we're trying to go around a turn, right? 100-meter turn, for example, radius turn, at a certain speed. Although we're going to figure out what's the maximum speed we can go at. What's happening in the y direction? Well, the net force in the y direction, well, it better be 0 in the end. Wait, is it going to be 0? Who knows? Who knows? We shall see. No, it better be 0, right? Because we don't want to slide. We don't want to, we don't want to take off or end up digging into the ground. Nor do we want to slide up and down, so there's clearly no motion in the up-down direction. So this is definitely going to be 0. What forces do I have acting vertically? Well, I have the net force acting up, weight acting down, the normal force acting up, or at least a component of it, the weight acting down, but then also the downwards component of static friction that I have to take into account. How do I know this? Well, I can look at it and look, it points downwards, right? It has a y component. No big mystery. So here I have Fn cosine theta, right? That's the vertical component of this one. Then minus mg, it's acting down as a whole, no components here. And then minus the vertical component of the static friction, so that's going to be its strength, SF, times the sine of theta. Now, one sanity check you can always do here is you should have cosine and sine, like one cosine, one sine, right? One sine, one cosine with each force, because you're taking different components. If you have cosine, cosine, we did something wrong if it's with the same force. Okay, so I don't know what my static friction is. I don't know what my normal force is. But if I'm given a speed v, right, some speed, here it is 20 meters per second, that's how fast I choose to drive, you could solve those two equations for the normal force and for the static friction. And that's it. Let's write this down. If v is given, it's fixed, then we could just solve these two equations for the normal force and the force of static friction. Right, two equations, two unknowns, very straightforward to solve. But that's what we're not doing. We are trying to find the maximum speed. But we want the maximum speed. We want to figure out how is our banking helping us go faster. We're going to find the maximum speed. Well, at the maximum speed, why is there a maximum speed at all? Because it's a maximum to static friction. So static friction is at the maximum. And so I know that this force of static friction is equal to mu S times the normal force. Right, that's how static friction works. That's the maximum. Right, if I'm not going at a maximum speed, this is not true. If I'm going at some speed, well, you plug in that speed, and there you go. Right, you can solve for the normal force and the force of friction. But if I want to go at exactly the maximum speed, I know that the force of friction is at the absolute maximum. The absolute maximum is this. So now I can take this and plug it into here and rewrite those equations. Let's do that. So make sure you have your notes. Maybe you should pause the video and try to do it yourself. What you're going to find is in the x direction, you have the Fn sine theta plus, now I'm going to plug in Fn mu s cosine theta, right? That's equal to mv squared over r. And I'm going to write VMAX now, because I've used the fact we're at a maximum speed where the friction is at the breaking point. Static friction is at the breaking point. In the y direction, I have that, well, my y direction equation looked like this. I'm going to write it as this is equal to the combination of those two. Actually, let's not do that. Let me go back on that. Let me just write it down as I've written it above. We can always rearrange afterwards. And I'm going to replace the static friction term with this. And that's equal to 0. So I've just taken those two equations we had here, and I substituted for the force of static friction the expression we have here, given that we are at a maximum. Okay, now I've eliminated static friction, right? Well, algebraically, because I've replaced it with the normal force times mu s, and mu s is presumably given by the road and the road condition, maybe the condition of your tires. So now all we have to do is we have to actually solve this for VMAX, right? When you come to a system of equations like this, and you've done some algebra, you're all confused. What am I actually doing here? Right, well, let's keep track. What are our unknowns? Our unknowns are the normal force, and our unknown is the maximum speed. We don't care what the normal force actually is. Right, we care what the maximum speed is, so we want to eliminate the normal force. So what I'm going to do is I'm going to take the y equation, take this, and I'm going to rearrange it for the normal force. Now you can do this. I trust that you can do this, and you should find that it is going to be this. Again, if you're confused, pause the video, do the algebra to get from here to here, right? Isolate the normal force. So now I can take this and I can plug it into my x equation. Plug it into the x equation. And I get the, well, it's going to be a bit long, but let's just go for it, right? I'm going to plug this into here. So I get mg divided by cosine theta minus mu s times sine theta plus, I'm going to plug this thing into here, right? I guess I'm going to have mg, I'm going to put the mu s on top just because it looks good, divided by cosine theta minus mu s sine theta times cosine theta. And then that whole thing is equal to mv max squared over r. Now, this would be fairly difficult, but not impossible to solve for theta, right? But that's not what we're doing. The angle here is given. Our traffic engineers build their road at a, say, 10-degree angle. So we can just plug in for theta if we have a specific value. But now we can just solve it for VMAX. So you can finish this at home. So solve to find VMAX, right? Straightforward, just rearrange. Take the square root to get rid of the square. You know what to do. You can do algebra. And let's give some sample values. E.g., our curve is still 100 meters in radius. Our mass I'm not going to give you, because what you notice is the mass actually cancels out because there's a mass in every term. We assume we're on Earth, of course, and let's suppose that mu s is, say, 0.5. It's a wet road, so it's lower, slide more easily. But you can also try, say, 0.9 roughly if it's a dry road. Again, the exact numbers depend a bit on what's the road made of, what are the tire conditions, and so on. So see what the difference is between the maximum speed you can go at. Theta, it's going to be fairly small. Let's go with 10 degrees. I think it's already a fairly big number for the angle that a typical road might be banked at. So see what you get. See what you find for the maximum speed. And if you go too fast, you're going to slide out and hit a tree. If you go too slow, well, it might be that the minimum speed is the minimum speed, but it might well be that the minimum speed is 0. As long as you can park your car on the incline, your minimum speed is 0, right? But in theory, if the angle is fairly steep, there could be a minimum speed, which if you go too slow, you're going to slide inwards. But usually that's not the problem, right? The problem is going too fast, so you figure out how fast can you go under these conditions. This was a fairly involved problem, right? A fairly involved concept, and we approached from different angles in different parts. We talked about what's the ideal banking angle, then for a given angle, how fast can it go. So make sure you make sense of all of this. Like, really take your time. It's worth it, because if you understand how to tackle these kind of problems, but also this way of thinking of how to set it up, what you're trying to solve for, then that'll also prepare you for a whole lot of other problems. Alright, thanks for watching, and I will see you in the next lecture.